start immediately with the second half of my talk, so I skipped the title. No, this is just to illustrate that the most powerful law in nature is Murphy's law, but that I guess most of you knew anyway. I do begin with the title, and I'll try to be a bit quicker with the rest. And the title, as you see, is To Be Announced. And working on the talk, I realized that was actually a very appropriate title. And the reason why it is a very appropriate title is effectively for the following reason, that I thinking about it, didn't quite know what I was doing in this particular workshop, because I have really not been working on liquid crystals for the past decade. And so for myself, I had to figure out what the title was going to be, and I think that basically what you'll find is that the title in this case is an emergent phenomenon. So in the past, I did work on simulation of liquid crystals when Tim Sluken this morning mentioned the spherocylinder as his favorite mesogen. It was also my favorite mesogen, at least simple, hardcore objects that would form liquid crystals. And I worked in that subject for a number of years. I always remained interested, but indeed, I for the past decade or so, I didn't do much. And what I really want to say is that if I look at how things have evolved, I see that there are certain new things that are coming up, but also I see that some of the issues that we were struggling with 10, 15 years ago really have become either much more interesting or have evolved in a different direction. And so, very briefly, what was I doing? I was working mainly on modeling of lyotropic liquid crystals, so the tobacco mosaic virus style things, where you have entropy-driven ordering, and you get all from the isotropic phase to the pneumatic phase already predicted by Onsager. You can get the smectic phase, you can get even the columnar phase, and all this doesn't require attraction. The only thing you need is excluded volume. Now, the thing I want to talk about is some of the questions that I think are unresolved, things that were predicted by simulations or hinted at by simulations, and where I think that either we have a very incomplete answer now, or we have a lot of controversy, or possibly we have an answer and I just don't know it. So I think that as this is a workshop, really what I try to do is to identify things that I find interesting to possibly discuss during this workshop. And the other thing, as I said before, very possibly if we get to the discussion, and the discussion I assume will be over wine, because that's the most important time constraint. So this starting up is one thing, but stopping is a hard constraint. Then we can actually see if there's things that I completely missed that have happened in the past few years that I was unaware of. Now, I will not be speaking about all kinds of liquid crystals, as you, even those of you who didn't know about liquid crystals when they entered this room this morning, by now they'll know that there are dozens and dozens of different kinds of liquid crystals, and they have all their own specific interesting behavior. What I will be talking about is specifically about bond-ordered phases, things that are really, I would say, on the whole, more on the crystal side of liquid crystals. And I will talk about something that is not strictly speaking liquid crystals, but I'll talk about liquid-like behavior in crystals. So I extend the boundaries of what I want to include a bit to go beyond what people would normally call liquid crystals. But let me first talk about bond-ordered phases, where we did some numerical work that at the time we hope would result at least in some experimental studies that would prove us wrong, possibly right, and neither has happened until now, and that is of course something that is disappointing, because it's bad enough if you predict something and it turns out to be wrong. It's even worse if you predict something and nobody bothers to check. So let me try to explain what the issue here is, and because I say here bond-ordered phases, I also say something about isostructural transitions. So I have to say a tiny bit about the phase behavior of colloidal particles, spherical colloidal particles that have a short range or a variable range attraction. And the nice thing about colloids is that actually, as an experimentalist, you can control the range and the strength of their attraction. And what happens is that the phase diagram of the colloids it's very much like the phase diagrams of atoms in space. So this is like Van 't Hoff's law. You have like atoms in vacuum, you can have particles in solution, and they have a pressure that you then call osmotic pressure. And as you increase the osmotic pressure, you can go from a gas-like solution phase to a liquid-like solution phase to a crystal-like solution phase. It's all the same, only on a much larger scale. And so here I have a very strange drawing of the phase diagram of a simple colloid with fairly long-range attraction. This is the density. As you increase the density, you go, depending on the temperature, at high temperature you have a fluid phase, and then you freeze, you get a solid phase. At lower temperature you get a critical point, and then you go a low density vapor phase, a high density liquid phase. Of course, these are all in solution. So this is dilute solution, concentrated solution, crystal in solution. And here below the triple point, there's only vapor and crystal. So that's the standard, I would say, argon style phase diagram. But with colloids you can do more. You make the range of attraction shorter, and what happens is that the critical point moves below the freezing curve, and you get only two phases, fluid and solid. Now even that's not what I'm going to talk about. What I'm going to talk about is what happens if you make the range of attraction very short. Not unphysically short, it's experimentally possible to do it. If you do that, then you get something that mirrors the liquid-vapor transition, but it's in the solid side. You get a transition between two solid phases that have the same symmetry, the same structure. For instance, phase central cubic. And the transition between them is only a different transition between phases with a different density. And in fact, that transition, that coexistence ends in the critical point, much like liquid-vapor that also have the same symmetry, and at some point end in the critical point. So this is a transition between two solid phases that that have a critical point, and this actually experimentally happens not for colloidal systems, at least not shown until now for colloidal systems. It has been shown for certain metals where if you compress them, there's a change in the electronic structure of the core, and you get a transition from, well, an isostructural transition between a dense and a less dense crystal phase. So cerium does that, for instance. I'll be talking about the situation where this is a two-dimensional or a quasi-two-dimensional system, and then you have here this critical point in the solid. Now, what does that have to do with bond-ordered phases? Important point is that if you have a critical point, density is the important variable, then the compressibility of that crystal becomes infinite, or conversely, the bulk modulus vanishes. Okay, now if the bulk modulus vanishes, and bulk modulus is called B, then in terms of the bulk modulus and the shear Lamé coefficient, that's the elastic constant that determines this deformation, you can express the Young's modulus, which is another quantity that is important, and is particularly important when in a minute we start talking about dislocations. Where the bulk modulus vanishes, the Young's modulus vanishes. Now, why is that important? Because there's a relation now between the possible vanishing of this object K and the existence of a hexatic phase. And a hexatic phase is a phase that has no long-range translational order, but it has quasi-long-range orientational order, in the sense that the memory of the direction between two bonds between particles, disks in this time, is correlated over very large distances, and that correlation decays algebraically rather than exponentially. So the scenario that you could have is that you have a 2D crystal. At some point you go through a transition where dislocations can spontaneously unbind, and you get a hexatic liquid crystal that is bond ordered, and then the second transition is needed to get you to the isotropic liquid phase, where you have short range bond order and short range translational order. Now, the dislocation unbinding, when does it happen? Very naive argument. There's two things that you have to consider. You have to consider the cost of making a free dislocation in a crystal, and in 2 dimensions that cost is infinite, at least if the surface area of the sample that you consider goes to infinity, then the cost goes to infinity, and it depends on the Young's modulus and some numbers. Actually, I left out the lattice constant, but I say suitably d-dimensionalized numbers. That's what you have to pay. What you get back is the entropy, kT times basically the log of the area. Now you can see that depending on the value of k, this prefactor is either positive or negative. If it's positive, the cost of making a free dislocation is infinite, in the limit a go to infinity. If it is negative, it's minus infinity. So at the point where this k over 16 pi is equal to kt, you have a transition where spontaneously dislocations will form. Now this argument is highly oversimplified, but mysteriously, in the end, that final conclusion about the value of the elastic, of the Young's modulus is still correct. Now curiously, if you have a situation where the bulk modulus vanishes, then this thing also would go to 0, and so that's what you expected, that hexatic, these dislocations will proliferate, and in particular, in this region where the bulk modulus is small. So it doesn't have to be just a point, but the whole small point where it's small, you should see a hexatic phase. Now, we actually then did simulations and showed that depending on, we did a very simple model potential, hardcore repulsion, short range attraction, this is the range of the attraction, and then depending on the range of attraction, you can get either a very narrow hexatic sort of bulge on a two-phase, so the solid, so this is a solid-solid transition, density, critical point, and here hexatic range, the black, here you have a much larger hexatic range, solid, and here actually solid liquid. And we did this in 1995, and then actually a second paper in 2004. And I have no time, I know that, but I can't help telling you this story. Why was there 9 years between the first paper and the second? Well, the answer was very simple. I thought we had published. And so actually, I'd been writing to Peter, we had been iterating the different versions of the manuscript, and at some point I said, it's fine, Peter. And he thought, okay, it's fine. And he didn't do anything, and I didn't do anything, until a visitor came and he said, by the way, did you ever check the core free energy of dislocation? I mean, I'm not going to talk about core free energy. He said, sure, it's in our paper. And I said, I couldn't find it. And so only then did I have to reconstitute the article from a postscript file, sort of take out the figures, put them back in. Okay, so that's what happens if you don't check what you've done. Anyway, worse than that, nobody has seen these phases yet. And that's what I, of course, would have wanted. Now, I could discuss how hard or easy it would be to see, because typically when people look for a hexatic phase, they try to see dislocation unbinding, which is pretty much the worst thing you can be looking for, but there are other things you could look for. Again, that's for overbinding. So, no experimental confirmation yet. Now, why has there been, because hey, come on, people have lots of colloids, they can easily make attraction ranges of the order of a few percent, so why haven't they seen it? Well, they haven't seen it because if the colloids have slightly varying sizes, and they always do, then that kills the transition. And so, I'll show you a picture, which actually, this picture is even worse, it hasn't been published at all, it was in the thesis. This picture shows this phase diagram with the solid-solid transition where the hexatic phase should be on top. And here you see what happens if you make the thing more and more polydisperse. And specifically, if you go to 1% polydispersity, this is for a fairly, well, not a 5% extension of the range due to retraction, you see that the transition has gone completely. Now, if you tell a colloid scientist, can you make a sample with colloids with a 5% polydispersity, they say, yeah, sure, I can do that. 3%, they start being a bit upset. But if you say 1%, they just say, go away, don't bother me, I don't have the time for that. And so this is the reason why it is not an easy experiment. I don't think it's impossible, it's just not an easy experiment. And I still think it's worthwhile, but it hasn't been done. Okay, other thing, this is for short range attraction. Actually, if you go for short range repulsion, that means a hardcore repulsion, and then a repulsive shoulder, maybe something you can do by putting some polymer brushes on the colloid, not too dense, then actually you make this transition more robust. That might be an easy route, hasn't been tried either. So that's one thing about the bond-ordered phases. Then there's another thing that has to do with bond-ordered phases, both in 2D and 3D, and I'll come back to this picture in a minute. This is just to show that some people, although not me, can make pretty pictures on the computer. I mean, usually as a computer simulator, you have to prove your credentials by showing by some color graphics, and although I can't make them myself, some people can. So actually the first in this case we looked at particles that have some intrinsic shape that might couple to the orientation, but not rod-like particles. So typically, if you talk about Onsager's model, then you have rod-like particles, and they can form, for instance, an ematic phase or possibly a smectic phase. But if you take square particles, this is a two-dimensional system, then at very high density, clearly, it will form a square lattice. Well, I say clearly, it's not quite so clear, but you can get this kind of lattice. As you expand it, you see something that looks still very much like a two-dimensional crystal, and then the lower the density, the more disordered it becomes. And here you see it clearly looks already quite disordered. And we were looking for the equivalent of the hexatic phase, where you have six-fold bond orientational order, but in this case we would expect to see a tetratic phase. Now, in these simulations we found evidence for a tetratic phase of hard squares, but the other reason why I found it, preparing this talk, somewhat disconcerting is that this is an article that appeared so long after the work that it was even worse than the other article where I just forgot that we had. I knew that we hadn't submitted, but it was almost impossible to communicate with the author who did the work. And so actually the work was done about 15 years before we published. And it meant that the system sizes that we were looking at were by that time already much smaller than the standard. But what we found is that, as far as we could tell, on the scale of the system, we had algebraically decaying bond orientational order with fourfold symmetry, but no translational or short-range translational order. So we found evidence for a tetratic phase. But then much more recently, actually last year, Mason's group at UCLA they can make squares. They have a lithography machine. I don't know whether this, but probably was done by lithography. You just put squares, you put them on the surface of or an interface, and then you look at the phase behavior. You see that this looks very much like the pictures I was showing. Crystal, a bit less crystalline, much less crystalline, etc. And they looked for a possible tetratic phase, and they said, no, there's none. So you say, oh, so maybe there was something wrong in these simulations after all. They were too small, I don't know. And then I think it is more about the last year, there was no evidence. There was a study by the group of Escobedo at Cornell, and they say, well, actually, if you look very carefully, these things, by definition, they were a simulation. They're mathematical squares, but these things are actually slightly rounded squares. You think, oh, what difference must it make? But according to Escobedo and Avendano, that actually makes a huge difference. And so they actually look here. They say, okay, let's make these squares by basically putting spherocylinders around a square. So the larger the aspect ratio of the spherocylinder, the more it looks like a square. So here you see this is effectively a circle, and this is effectively a perfect square. And there's all kind of phases happening, but this tetratic phase only seems to happen in a regime where you have really very sharp corners. So somewhat surprisingly, this phase is not very robust if you make the particle slightly rounded. So in the end, I don't really know what the situation is. It may be that the experiments happen to be in a regime where you couldn't see the tetratic phase, and if people would take slightly more sharply pointed squares, that they could see it. But at the moment, that is an unresolved issue. So that's another unresolved issue. Now, there's one thing that I like to point out in general, and that's that if you look at, for instance, hard disks, people have been looking at the phase diagram of hard disks since the 1950s. Someone older and Wainwright studied it. Actually, Metropolis in 1953 already was looking at hard disks. So that's pretty much the very earliest system that people looked at with computer simulation were hard disks. Initially, people thought, this is in the mid-60s, that the transition from solid to liquid was first order. And then when people were aware of the possibility that there might be a hexatic phase, there was a long period of confusion as to whether or not there is actually a hexatic phase in hard disks. I don't quite know how to summarize. I know that there's all kind of TV cameras pointed at me, so I have to be very careful how I phrase it. But I think that probably the consensus is that there may well be a narrow hexatic region separated by a first order transition from the isotropic phase. But if the hexatic phase region is there, it's a very narrow density range only. Now, as soon as you go to non-spherical particles, like for instance these are two-dimensional ellipses, it turns out that it is extremely easy to make bond order phases. So it actually becomes extremely hard to have real crystalline phases. So here you see a crystalline phase, and again, it's something that we looked at not in much detail, but if you look at these crystalline phases, it turns out that it's not so obvious that they're a crystal phase. And so you all know this picture that says that this is not a pipe, and similarly, I would argue that this is not a crystal. Now, why do I argue that that's not a crystal? A crystal should have long-range translational order. And these things have absolutely short-range translational order. This is not a crystal. So it looks, you see all kind of nice layers, but it is not a crystal. And clearly the thing is bond ordered. I would be a bit hesitant to call this a nematic phase, although actually probably on sufficiently long length scales, this is what you would call a nematic phase. But bond order for non-spherical particles you see everywhere as soon as you go to non-spherical particles in 2 dimension. Now there's actually another way to make these tetratic phases with 4-fold orientational order, and that's by taking not squares but taking rectangular particles. And so, as we are in the mathematics institute, I know I have to write something on the blackboard. I mean, otherwise this is not acceptable in the mathematical community. So you take a particle like this, and if you have a second particle like this, you have a square. And so you can imagine that the thing could also do this. And so if you can tile space in any way you like, and for entropic reasons, any of these arrangements would seem to be equally likely. It's not quite as simple as that. I'll come back to that at the end, or maybe not. But you can see that this kind of particle could form a tetratic phase by making the proper use of the fact that 2 of them together are like a square. And in this particular case, there was work by Daan Stillinger and Torquato, where here you see a blow up, you see these things. They're not always, sometimes you see a whole row of them, but they computed the G of R diffraction pattern, and they see a 4-fold symmetry in the diffraction pattern, which suggests that actually this is a phase with 4-fold bond order. So in this case, there seems to be clear evidence that you'll have bond order in a 2-dimensional system. Now, this is all 2 dimensions. Now about 3 dimensions. Are there other liquid crystalline phases, symmetry-wise, that have no translational order but have higher order orientational order? So we know nematic, so there's up-down symmetry, but they have cylindrical symmetry. But in principle, there could be higher order things, so that, for instance, you don't have a 2nd rank tensor order, but a 4th or a 6th rank tensor order. And in fact, in theory, and I'm now talking about theory at the real Onsager limit, the answer is yes. If you could make a particle that is 3 perpendicular rods, and you go to the Onsager limit, which means infinitely thin, infinitely long rods, then at some point these particles start feeling the excluded volume of each other, but because they are in the Onsager limit infinitely large aspect ratio, the volume fraction occupied by these particles is still vanishingly small. So these particles can't freeze because that they only do when they occupy a large fraction of the volume. They do get excluded volume effect, and actually they can't form a nematic phase because there's no preferred direction. So all 3 axes in this case are equally long. And so what they actually do, they'll form a cubatic phase, a phase with if you wish, in the Legendre polynomial language, a P6 orient, or actually a 6th rank bond orientational distribution. And so it's easy to show that this should happen, but and the only thing is that in practice it doesn't happen so easily, because you have to go to really very high densities, and density in this case means the number of particles in a volume L squared d, which is order the excluded volume. And that number of particles has to be of the order of 50, and at the same time you wanted the number of particles per volume, which in these units would be a number of particles in the volume LD squared, is still very, very small. And to get that, you need huge aspect ratio. So you need this limit, and that means that it's extremely difficult to get, and so there are no experiments yet. And I think that in this case, it may be very, very difficult to get experiments. I should also say that other shapes will do the same. First of all, it makes no difference exactly how these rods are connected, whether they're connected in the middle or end on. This is just because it looks nice. You can also make other connections. You can also make tetrapods, which actually with short arms have been made experimentally by Alifasatos at Berkeley. If you take tetrapods, if the tetrapods would have very, very, very long arms, they would form a cubatic phase. But again, it's going to be extremely difficult to do that. So these are things where, yes, in principle, we know that they should form cubatics, but experimentally it's going to be hard. Yes?
Yeah, there was this work by Parsigian and co-workers where they had DNA, but there was a pneumatic axis like this, and then it had hexatic order perpendicular.
Yeah.
So that's three-dimensional bond order. It was not crystal.
Well, it's 2 plus 1 if you wish, but yeah.
Well,
yeah, no, that's right.
2 plus 1 is always 3.
Sorry?
2 plus 1 is always 3.
I thought that in some branch of theoretical physics, 2 plus 1 is not 3.
John Toner pointed this out a long time ago.
Yeah. No, I think that's right. So this is
a cubatic phase doesn't have any interesting scattering.
Yeah.
Compared to isotropic.
No, that's a real problem.
But pneumatic plus hexatic does.
Yeah, I think that's right. Thank you. This is another system where this is that has a behavior that we don't really understand very well. So let's go back to this drawing. Here I was drawing rectangles in 2 dimensions and said they can be oriented like this or they can be oriented like that. If you do the same thing in 3 dimensions, you take particles that are like a stack of coins, then you compress the system, then there is a region in the phase diagram where they seem to form this kind of phases. You had stacks like this, stacks like that, and stacks in the 3rd direction. And at the time when we did the simulation, but this is a long, long time ago, when we had really small systems and computer time that's according to Moore's law is about 10,000 times less than what you can get now. We concluded that these structures were compatible with cubatic bond order. If you take a slightly, these particles actually are not, they're not really coins, they're truncated spheres. So they're sphere, you cut it off the top and the bottom, and then we got this cubatic order. We then looked at cylinders. We thought cylinders may be easier, and actually we found no evidence for cubatic order in cylinders, even though it looks superficially like they might do it. And then there was a very extensive study, well, actually last year by Marjolein Dijkstra and her collaborators, where she looked at all possible, like cylinders, truncated spheres, and spheroplates, and they found that if you really look at it on a sufficiently large length scale, that no, they are not cubatic. These cubatic phases do form kinetically, but then they go on to form a stable columnar phase. So in this particular case, for these specific shapes, it looks like you don't get a cubatic phase. But it doesn't mean that you don't get a cubatic phase at all. It may be that you just need another shape. So the next obvious thing is if you say, okay, like if squares form tetratic phases, why wouldn't cubes form cubatic phases? And so this was a part of the controversy where I was not personally involved in, so I feel somewhat freer to speak about that. Actually, there were some early simulations by James Elliott and Alan Windle, where they found that if you take cubes, they do form what looks like a cubatic phase, but this was a relatively small system. Then, much more recently, again, Escobedo's group did a study of many different systems, but one of them was the cubes, and he found that there was a region where this system seemed to have no long-range translational order, but it did have cubatic order. But then again, there was a study by Marjolein Dijkstra and her collaborators from Smallwork Chlorophyllium, and they found actually that there probably is not a cubatic phase. They couldn't completely rule it out, but they said actually what you find is something that looks in some ways like a liquid because particles diffuse very rapidly, which is something that Escobedo, etc. had also noted. But if you look at the single particle density, it is periodic in the normal way that you would expect for a crystalline solid. And I should also say, but Sharon can correct me if I'm wrong, that Damasceno et al. Last year looked at how many shapes? 200? I don't know, a huge number of shapes. And they found that if you take cubes, but you go to really high densities, that they form a crystal, which I guess is what you expect And I don't think that you investigate the lower density behavior, but so you
well, we did look for the cubatic phase because of Escobedo's work, and we definitely don't reproduce his results, but we reproduce Dijkstra's.
Okay, good. So this still leaves the overall question: do stable cubatic phases exist? At the moment, I really don't know the answer. I want to end. I really thought I go quickly now because I see the wine standing already over there. With something where you see liquid-like behavior in crystals, and in order to do that, I actually have to. So actually, maybe I have to skip some things anyway. I have to go back a bit, back a bit, and talk about how you fill a lattice and what a crystal actually is. Because if you have a crystal of particles with a hard core, it doesn't have to be completely hard, but to be sufficiently repulsive core, then this could be, I don't know, indeed colloidal crystal. It could also be a metal or something like that. Then under normal circumstances in equilibrium, you fill effectively all lattices. Not all of them, because there are vacancies and there's also interstitials. But if you have soft particles, that is not true. And actually, as you see at the end, it's not even true for all hard particles. So what's an example where you don't fill all lattices one-to-one? The example is cluster solids. And to explain cluster solids, I use an analogy that I find very helpful myself. And so, because we all travel by air. And so we know what happens if you go to an airplane. I want to warn you about what happens if you apply science to airplane design. So this is the way we don't travel, but some people do. So you have these chairs and use this, and you get a bottle of champagne. It's like a Christmas party all year round in royal class. But of course, in order to make the chairs, the seats cheaper, you get a business class, you get something where you can even unfold your laptop, which is not, of course, the way we usually travel, because there we sit like this. And that is basically because the airline companies have decided to decrease the lattice spacing to get more of us in. Now about the risks of applying science. If the airlines ever find out about the work of Christoph Likos and Hartmut Leuben and their collaborators, then future is going to be far worse, because then you'll have cluster class. And in cluster class, as you see, you just assume that people can interpenetrate, you just put them on the same seat. Now, this is precisely what happens if you take particles with a soft interaction. So you can do two things to increase the density of a crystal. Either you decrease the lattice spacing, or you would put more particles on a single site. And this, for instance, happens if you have a potential like this. And this is a repulsive potential. It is bounded, so it doesn't go to infinity at 0. And importantly, actually, another condition is that it should have a Fourier transform that has a negative part. So it can't be a Gaussian, but if it's a bit flatter than a Gaussian, like e to the power minus x to the power 4 or something, then it can form a cluster solid. And actually it does. So this is what Bianca Mladek, who worked on this already for about a decade, has found that for these particles, you see many particles clustering on a single latticite and interpenetrating.
But a variable number.
A variable number, yes. So not all lattices have. At low temperatures, it's either 1 or 2, etc. At high temperatures, it's fluctuating. And well, this is about the Fourier transform. This is about the paper that I don't want to discuss. This is the simple argument why they form. It's very hand-wavy. This is the potential, the repulsion of different particles. Now you say, where can I put the next particle? If it's a Gaussian potential, you put it where the potential is minimum. That's in between. If it's flatter than Gaussian, actually it turns out the minimum is exactly on top of another particle. That's a very rough argument that gives you a feeling for why you would ever get clustering. And it's easy to work out simple examples that show you the clustering actually should happen. Now what's the interesting thing? Normally when we talk about the crystal and we say we don't really distinguish carefully between the number of particles and the number of lattices. But here you can't do that, because if you look at the variation, the free energy, then you can vary by changing the temperature, the volume, the number of particles, but actually also by varying the number of lattices. Now you have to be very careful with this, because this term is a bit special. In the end it will go away, and the reason why it will go away is that the crystal, of course, searches that number of lattices that minimize the free energy, and therefore the coefficient is always 0. It's a bit like if you have particles in contact with a reservoir, that can be deleted and created, chemical potential has to be 0, because that's the situation where the term in front of the variation number of particles is 0. So, but in principle, it's certainly in a simulation, if you're not careful, you end up with systems where you've prepared a certain number of lattice heights, it has a finite μc, and all hell breaks loose and you get nonsensical answers. So what we did at that time is to do calculations where we carefully made sure that we did the simulations such that this chemical potential associated with the number of lattices was 0, and then you can compute the phase diagrams, and actually in this case it would have a fluid, it would have a BCC crystal and an FCC crystal, and there's theoretical density functional theory prediction, and for the freezing it's fine, and for the solid it's a bit less fine, but actually pretty good. But the main thing is that actually then you can compute the phase diagram. Now this is just to show lattice heights and particles are not one-to-one mixed. I mean, it's not quite as bizarre as it sounds. If you have a crystal of micelles, it's the same. So it's correct?
Blue phase.
The blue phase. Actually, even a colloidal crystal. I mean, if you look at the water, can go from one lattice. So I mean, it sounds a bit.
Micelles also go from BCC to FC.
But of course, but to have these big particles on top of each other, that's a bit more bizarre. So cluster solids, they're real crystals. They have long-range translational order. There's no long-range, no one-to-one correspondence between the number of lattice sites and the number of particles. Density fluctuation, it's a bit like the smectic. You have two ways you can do density fluctuations. You can vary the density by changing the lattice spacing, or you can do vary the density by having particles permeate from one cell to the next. So if you wish, you have two sound modes. So that's an interesting thing, that if only these things had ever been made, it could be measured experimentally, but until now, there's no evidence, at least no evidence for molecular systems. Again, there's a special case. If you take a two-dimensional electronic system, so a two-dimensional electron gas in a very strong magnetic field, at a quantum Hall step, you get electron bubbles, and they can contain, they're basically electrons in their Landau level. The interaction between electrons in their Landau level is very much like this truncated Gaussian, and so they can have 1 or 2 or 3. Unfortunately, you can't follow the whole phase diagram, because by the time you get to the critical point, actually the thing gets out of the I think they go into different phases, so you can't actually follow the whole thing. But for molecular systems, there's predictions that dendrimer should do it. I'm not aware of any convincing experimental demonstration yet. I'll wave at the camera again. So, okay, so now even for normal crystals, the number of lattice heights is not equal to the number of particles, but that's because of vacancies in the interstitials. That is trivial, and for most simple one-component crystals, the vacuum concentration is really low. Even at melting, it's typically of the order of 1 in 1,000 or less. Surprisingly, that is not always true. And that's where I really that's the last thing I want to show. And this is the hard cubes that Marjolein Dijkstra and her group studied to look at the cubatic phase. And they did a simulation. They made a 40 by 40 by 40 lattice of cubes, and they looked at the density, and you see it's perfectly ordered. This is an average density profile. And then, I don't know how they ever got the idea. They started counting the number of lattice sites, and it was 41 by 41 by 41. The system had spontaneously generated vacancy. So this is an amazing thing, that although it's perfectly ordered, actually this thing is full of vacancies. And actually at the melting position, this system has almost 7% of all lattice sites not occupied. I mean, there's no, to my knowledge at least, in a pure system of simple atomic molecular system, there's no equivalent. In mixed systems, yes, if you go to superionic conductors or whatever, yes, there's all kind of examples. But for pure systems, there's nothing like this at all. And it makes a difference for the phase diagram, but I'll not go into that. As you go to high density, you squeeze out the vacancies. Now this is a snapshot, and the snapshot shows that actually you can't see the vacancies, and you can't see the vacancies because they're delocalized. And that tells you something about the mechanism. Cubes don't interdigitate like spheres, so they can slide. And so if you have one vacancy, it's a bit like this game where you have to move letters into place. You basically have one vacancy in a line, and so that you gain free energy, or you gain entropy, by having the whole thing delocalized over the entire line. And so this, what you see, is a delocalized strip of particles that together could concentrate somewhere to form a vacancy, but they don't. And actually, to me, this is another liquid crystal problem because the length of these things, how long should they be? Well, they can't cross another one. So it's a bit like a liquid crystal model, the Otsansic model of rods that are perpendicular but it can't cross. And I think that all systems where lines can slide like this should show similar behavior, but at the moment there's very little evidence yet. So particles can diffuse very rapidly because of these lines. The metal is a crystal and should therefore have finite elastic constants. And as before, there's no experimental observation yet, at least not to my knowledge. So I showed you the 2D squares with vacant with the tetratic phase. We haven't looked at that time. We didn't look at vacancies. If I would do it again, I would certainly look at vacancies because I would expect to see even more of them. I think I've come to the end. The reception is waiting. And so I'm summarizing, and the summary is that I think that there's really a lack of experiments on these unconventional lyotropic liquid crystals, or non-spherical particles that can form interesting phases. I think there's also a lack of theory. Many of the things that I described have no solid theoretical underpinning, except from a purely at a phenomenological level. And I think there's even a lack of simulations, which means that even my community could do some useful work at some point. And with that, I really would like to thank you for your patience.
Well, thank you very much, Dan. You seem to have done an excellent job in squeezing your talk into a slightly smaller space than experiments might have.
The vacancies have gone.
Are there any quick questions before the...
Just a quick comment. Did you know the work of Jacques Pro and John Toner about the pneumatic island?
Yes. That's okay. Sorry, what Tom is referring to is that there is I mentioned the solid-solid transition with the hexatic bubble around it. There's much earlier work by Jacques Pro and John Toner where they looked at a smectic transition that ended in a pneumatic island or lake, whatever you want. So it happens more often. And yes, I don't know what there's experimental evidence, is there?
I think there is.
I think there is. Yes.
Right. And then there's a pneumatic critical point in the bubble.
Yeah.
So having rounded corners prevents the tetratic phase. In general, when should we worry about structural details like that? When are they important?
I have no general answer to that question. I mean, of course, the typical physics approach is to say all these details shouldn't matter. But I mean, now I'm head of a chemistry department, and they always tell me that the details do matter. So I'm a bit torn.
Yeah, for making a tetratic phase out of rectangles. Right, yeah. the lower symmetry particles. Right? So you told a story there which was based on one detail, right? Which is having the 2-to-1 aspect ratio of the particles. Yeah. I think it's more general than that, right? That regardless of the aspect ratio, for particles that are close to being square, but not square. Yeah. There's a tendency to make tetratic phases that won't have unit cells that are specifically looking like that, right? And I worked with a student once on a Myers-Alpha style theory of that sort of thing, right? So I think there you can wash out that kind of.
No, actually we did this actually with Bates. We did a calculation already about a decade ago on spherocylinder with various aspect ratios, and at least locally they formed things that had very much this tetratic-like structure. We didn't find any long-range tetratic order in those systems, but then they had rounded corners.
Well, thank you, Dan. Let's thank again all today's speakers.